Hi, everybody. This is Mandy Moeller. I'm going to be discussing primary congenital hypothyroidism today. It's the topic I've been covering throughout the course of the last 8 weeks. A pretty interesting genetic disorder, and so I'll just take you through that. Some of our discussion points today, I want to cover off on the description of the disorder, some of the major characteristics and symptoms, also the molecular cause of the disorder, also rolling into the protein function and mutations, mode of inheritance as well, with some example Punnett squares and an example pedigree as well, in addition to the genetic testing for the disorder that's available, and then just a quick slide on some references where I got all of my information. So just to go through some of the major characteristics of this disorder, obviously considering it's called primary congenital hypothyroidism, obviously affects infants from birth, so that's why we call it congenital. It is the partial or complete loss of function of that thyroid gland. You've probably also heard of it being called goiter and some other things like that. But that thyroid gland is what makes hormones that help us grow and develop from a from birth, from a very young age. Also helps with metabolism. And basically, this disorder causes lower than normal levels of these hormones that we need to develop normally. So affected babies may or may not show symptoms. Some do, some do not. The ones that do are typically a little less active and may tend to sleep a little bit more. They may also have difficulty feeding. They may have some constipation and some very extended bouts of jaundice as well. This disorder can lead to quite a bit of an intellectual disability and very, very slow growth. Many of us are probably pretty familiar with this, or may even know someone who has this disorder. Can also occur as part of kind of a secondary condition to other situations or other syndromes or other types of things that are affecting us via our other organs or tissues. So this can be a secondary disease as well. And just a few examples listed here. The molecular cause of this disorder, most common, is just that shortage of that iodine. We talked about the hormone development and creation by that thyroid gland, and the shortage of the iodine in the mother and in the affected infant is really what is most commonly causing this disorder. And that iodine is essential for the production of those hormones that we discussed. And it's said that genetic causes do account for close to 20% of the cases of this disease or this disorder. So I thought that was actually really interesting. In addition, I found this really great graphic that kind of talked about primary congenital hypothyroidism, and it really went through a nice flow chart of, how to establish the severity of the hormone defect, how to investigate for various parts of this disorder, how to determine the morphology, and the positioning of the thyroid gland and how that impacts everything. So I thought this was a really nice graphic that really laid out the genetic side of this disorder. In terms of the function of the proteins and mutations, the normal protein, the TSHR is the receptor, and that is known as TSH is the thyroid stimulating hormone that we're all familiar with. It is a member of the glycoprotein hormone family, and what happens is the anterior pituitary gland releases TSH, and it's the main regulator of the thyroid gland growth and development. So if the TSH does not bind to the TSHR and does not stimulate thyroid epithelial cell proliferation and doesn't regulate these things, we're not going to have the synthesis of the thyroid hormones that we need for proper development. And so a mutation is going to change one of the amino acids used to make that receptor. So then as a result, we're going to have the receptor continuously activated and overstimulating the production of those thyroid hormones. In addition, a little bit more about mutations here. These are the 5 genes that have, in all of the research I did, came up over and over and really dominated the research around this disorder, and are really said to be the primary causes. And then in terms of the mode of inheritance, when this results from mutations in some of these genes, the condition has what we call an autosomal dominant pattern of inheritance. And what that means is that we've got one copy of the altered gene in each cell, and that's all we need to cause this disorder. So in some cases, an affected person may inherit the mutation from one affected parent, but in other cases, the condition results from a brand new mutation altogether that would have been formed in those reproductive cells or at some early time in the embryo's development. So it can be inherited or it can be developed from a brand new mutation. These were just a few example Punnett squares that we had done earlier in the semester that I thought really demonstrated the different genotypes, phenotypes of this disorder. So for example, if both parents are affected with the disorder, there's going to be a 100% chance that all offspring are going to be affected. Now, on the contrary, if one parent's affected and the other parent does not have the disorder and is not a carrier, then all of the offspring will get an A dominant or an afflicted allele, one or the other. So they'll have both of those. But none of those offspring will be normal since, like I said, that this disease is autosomal dominant. If one parent's affected with the genetic disorder and the second parent is what we call a carrier, then the carrier parent's going to pass on that allele, while the affected parent's going to pass on just the capital A. So then moving into if neither parent is affected with the disorder and neither are considered a carrier, then the probability of offspring being afflicted with the disorder is 0. This is just a very simple pedigree that I put together to also demonstrate this autosomal dominant inheritance pattern. So the non-shaded are expressing the recessive phenotypes. Actually, that should be dominant phenotypes, sorry. The shaded individuals will be either capital R small r or capital R negative. The males and females are equally likely to have the trait, and there is male-to-male transmission. So those are a couple of differences between this disorder compared to some of the other disorders that we read about and that some of the other students in the class are discussing. That same chart, but a few more points I just wanted to make here is if the parents don't have the trait, their children should not have the trait, except for some of the instances that we discussed prior. The traits do not skip generations typically. If the traits displayed in offspring, at least one parent typically is going to have the trait. And if the trait's present wherever the corresponding gene is present, or it is, let me say that again, the trait is present wherever the corresponding gene is present. So if both parents possess the trait, but it's absent in any of the offspring, then both parents would be carriers or heterozygous of the recessive allele. And then homozygotes for the dominant condition have a much more severe form of the condition than the others. In terms of genetic testing, just a little bit of quick information here. Screening for this condition in newborns is required in most of the first world countries for sure, the US included. There are blood tests, so we basically are looking for a T4, that thyroid hormone and how much of it we have, and then also that TSH hormone. Those are the most common items that we look at to confirm a diagnosis of this disorder. It does take the form of a combination of those two measurements, typically. It is, as I said at the bottom here, the preferred method to use both of those, but it really depends on the infant's existing TSH levels. So if they have a high TSH level, a primary TSH with a backup T4 is going to be used, and vice versa. But if both of them are relatively the same, then that preferred method of using both would be completed. In addition, they do recommend that the testing be completed in the first 2 to 4 days of life. They really don't like you to wait any longer than 7 days to do this genetic testing on these infants. Because the early detection is what's really important to get this diagnosed and get the treatment going immediately in order for the infant to have the best chance at developing normally. And because this testing can be accomplished by some pretty common medical tests, as I said, the T4 or the TSH, testing those levels, any hospital or medical office can complete this testing. There you can find pretty much any pediatric endocrinologist that can diagnose these types of things. There is still, of course, some controversy around the topic, around the testing centers for a variety of reasons, mainly because it could be that the preterm infant or infants with very low birth weight may be their results may be skewed just due to those items, and the thyroid stimulating hormone TSH that we've been talking about, if it's not typically elevated in central hypothyroidism, so you have to just use an algorithm and give it their best, basically a best guess for diagnosing and management of this, of that. So, and hypothyroidism can be acquired later. So early screening, while it's required, and they do a really great job of catching this really early for a lot of infants, some people argue that it's unnecessary because there's always the chance that they could develop it later. And here's the references that I used throughout the semester and in my presentation today. So thanks for your time.